Okay, stats kids. There are two sections in chapter 11 that we're going to talk through before we start our semester project here in a couple days. And so the first one is section 11.1. And this is just, I don't know, kind of an easier, hopefully, section that has to do with hypothesis testing still. So we still have like our bell curve. Let me go down to an example. Bell curve, our null and alternative hypothesis. They look a little different this time, but hopefully this is pretty straightforward and isn't too bad for you. Some of these examples look kind of confusing, but they're not too bad. So this is this section of goodness of fit. So we're trying to like look at, like, this first example is rolling a dice. And the outcomes of rolling a dice are getting a 1 through a 6, right? Like those are the sides that are on a dice. And what we would say is, like, depending on how many times you roll the dice, like you would get a 1 out of every 6 times. You would get a 2 1 out of every 6 times. You would get a 3 1 out of every 6 rolls, that type of thing. And then we compare that to what we get when we actually roll the dice that many times. So we talk about an observed frequency versus what we can expect. And so the goodness of fit is talking about like how the data fits, and comparing those percentages, like the observed versus expected, to see if this is a fair dice or not, and those types of things. So they talk about like goodness of fit. As a hypothesis, the observed frequency fits some claim distribution, so it fits, what we expect to happen. And so we have a formula that we're going to do for our test value here. And this goes on our chi-squared chart. So you're going to have to locate him. Chi-squared. If you have that chi-squared chart, it's on the back side of the T chart that we have. So it's just that single-sided chi-squared value chart. It looks like an x squared. And then this is what we will calculate for our test value, okay? So we'll go down and do that here in just a little bit, but we're going to talk about calculating expected frequencies first. So when you're doing an expected frequency, they give you a little formula for it, which, like they say, it's called N over K. And let's talk about what that is here. You don't really have to think about the formula too much if you just go with what the problem is asking. A says if you roll a dice 45 times, okay, with the following results, assuming that the die is fair and all outcomes are equally likely, find the expected frequency for each empty cell. So what actually happened was when we rolled the dice, a number 1 showed up 13 times. The 2 on the side of the dice showed up 6 times. 3 showed up 12 times. 4 showed up 9 times, etc., like all the way through there. But if we rolled it 45 times, how many times should it show up a 1? How many times should it show up a 2, etc., right? Well, if this is a fair dice and all of the sides should show up with equal frequency, we would just take 45 and divide by 6, right? So that's what they're getting at with the N divided by K. N is the number of times we're rolling the dice, and K is how many sides or how many options we have. And that's going to give us the expected frequency. So if I take 45 and divide by 6, I get 7.5. Okay, I could have done that in my head maybe, but anyway, 7.5. So I could expect that if I rolled the dice 45 times, that each option should come up about 7.5 times. Now, obviously, you can't get a 0.5 of a roll on a dice, but 7.5 times is the average of how many times a 1 should show up if I rolled 45 times, how many times a 2 should show up, etc. And then we just compare and see, are there any discrepancies between the observed and what we actually had happen? Like, is this leading more so for a rigged dice or whatever? And we can kind of compare that using those percentages, okay? So that was just calculating what the expected frequency was in part A, okay? In part B, we're assuming that this is a loaded dice or not a fair dice, and they're saying that the probability is going to be 50% show the time it's going to show up a 1, and then 10% of the time it's going to show up as all of the others. Okay, so that is going to help us determine the expected frequency, and then these numbers are what we actually got. So ignore those numbers for just a second, and we're going to figure out of 45 times, how many times should it come up a 1 if it's a loaded dice. Well, if it's 50% of the time it's coming up a loaded dice out of 45 times, 50% of 45 is like 22.5. So I should end up getting a 1 22 and a half times. Okay, 10% of 45 is 4.5. 10% of 45 is also 4.5. Okay, so this is when it's not a fair dice, when it's not equal, going all the way across what should happen. So this is our expected, what we can expect to happen based upon the percentages of the outcome. What actually does happen is these numbers, okay? And then we can look and see like, okay, if it was a loaded dice, this is what should happen. So is the results that I get here in the middle, is that leading more to believe that it's a fair dice? Is it looking more like these numbers? Or is it looking more like the bottom numbers, where it is kind of one-sided? Favoring the side that has 1 on it. So that's something that we have to decide, and that's what we're going to be doing with finding our test value here using that formula, and doing our bell curve and our hypothesis testing and stuff like that. Okay, so that's the first thing that we have to do, is calculating the expected frequencies. Out of how many should we get this many? After we fill the table in, then we can go ahead and do our formula here. Okay. All right. So I'm not going to go through this chart because we know the whole fail to reject and reject thing. The only difference is we are used to filling out our bell curve with 2 sides. And the deal here is that we really are only going to end up looking at the right side here, because when you look at this formula for our test value, when you take the observed minus expected and you square it and you add those all together, this is not going to never give me a negative number. Okay, so that's why when they fill out this bell curve, and we decide whether we're going to fail to reject or reject, we are only going to be looking at the right tail, because we'll never have negatives based on this formula, because we're going to be squaring and taking a sum. So that's kind of why you see this diagram here if you're confused. We still will have to look at our chi-squared chart to find where that cutoff mark is, and then we're just determining, is it over here or is it over here? And that's going to tell me fail to reject or reject. So if I have a number based upon my cutoff value, if I have a number over here, then that's going to give me a fail to reject. Okay, we're going to say that it's, and we'll talk about what fail to reject looks like here in a second, but fail to reject will be on the left side, and then reject would mean he is in the extreme values. Okay, so he's on the right side there, and that would give me a reject the null hypothesis. Okay, and we'll talk about what that looks like. So here's the deal. Let's go through. I'm not going to read this whole paragraph here, but I'll kind of explain to you and paraphrase what it is they're talking about. And so let's circle some things that are important. We have 100 weights of people in California. Okay, so they asked 100 people in California how much they weigh. Okay, doesn't really matter. We don't really care how much they weigh. What they're recording here is okay, pay attention to this because this is kind of hard to digest, is the last digit of their recorded weight. So for example, if we have somebody who is 197 pounds, we are recording that their final digit was a 7 and they would live in this category. Okay, if you were recording that your weight was 142 pounds, you would be living in this category. Okay, now the reason why they do that is because if you ask somebody their weight, okay, it's probably not likely that they're going to come and tell you 142 pounds, right? They're probably going to round to the nearest like 5 pounds. So they might round it to 140 pounds. Or if you're a girl, you're going to take off like 20 pounds and you're going to round it to like 125 pounds, something like that, right? Like that's just what we do sometimes. So, what we're trying to see is like, did they round or did we actually get an accurate data? So looking at these numbers right here, if we look at the frequency of how this is working, right, we notice that 45 people reported 0 as their last digit. So like they reported like 140 or 150 or 160 as their weight, right? Like their final digit was a 0. We had 30 people record that 5 was their last digit. So like 145 or 155 or 165, ending in a 5. Okay, and then all of these other ones are not happening very often. Okay, so what this can be used to determine is the method that I collected this data, right? So if I actually had a group of 100 people and I brought them up and set them on a scale and recorded their weights and the final digit of their weight, these numbers would probably be a little bit more even, right? So I would have a lot of like zeros. I would have more people that were reporting like in the ones, like 141, 151, 161, those type of things, okay? But what's happening to this data is the fact that I have a lot of people in this category and a lot of people in this category means that I'm probably not recording their data by me actually measuring it. I'm probably just asking them for their weight and they're just reporting it to me, meaning that they're rounding to the nearest 0 or 5 pounds, right? That's just kind of how you do that. And so we can tell from this data that it was actually reported to us data, like they just guesstimated what their weight was and reported that to us rather than me actually gathering the data by having them come up and stand on a scale. Okay, so it says down here, it says, so a weight of 197 might be rounded and reported as a more desirable 170, right? Because a lot of people lie about their weight and that's just a thing, right? So if we, in contrast, if people are actually weighed, the weights tend to have last digits that are uniformly distributed, meaning they're all the same with last digits of 0 through 9, versus if we just ask them their weights, it would be reported as a 0 or a 5 as their last digit more often. Okay, so that's kind of what we're looking at here, is like we're looking at, are these equal frequencies? And you can kind of tell that like, no, they're really not equal frequencies, but we're going to run a test on it and see if they are. So what our hypothesis test looks like, I guess one thing before we get to hypothesis testing, if they don't report and tell you what significance or fish value to use, go ahead and use 0.05. I don't know if I do that every problem on your homework assignment if I tell you what fish value to use, but go ahead and do that 0.05 if I don't. Okay, so our hypothesis test is going to look like this, and we use P's for each one, okay, because we're talking about like proportion. So the proportion of people that reported 0 as their final digit, the proportion of people that reported 1 as their final digit, and 2 and 3 and all the way up through 9, right? We're saying that those proportions are all going to be equal to each other, meaning that like there is the same number of people in each category approximately. Now we know from this data, obviously this one and this one look bigger than that, but that's what our hypothesis test is, okay? And we are testing the claim, if I go to this part, test the claim that the sample is from a population of weights in which the last digits do not occur with the same frequency. So actually, we are not claiming this one. We are actually claiming our alternative hypothesis, which is that they are different from each other, right? Because we're saying that the 0 and the 5 are showing up more often. So this is actually what our claim is, if you want to put claim next to him, okay? But we always start, again, with our null hypothesis being the equal one, right? Okay, so this time we just have 10 things, actually, that are equal to each other, okay? So what we need to do is we need to go ahead and find this guy from our formula, and then we need to find what our critical value is. Okay, so this is our test statistic. This is our test value. And then our critical value is going to be the number from the chart that we look up. And then we're going to compare those guys, and that's going to tell us which one of these hypotheses that we go with. Okay, so here we go. Let's go ahead and do the calculations. And some of these can kind of be a little icky, but we'll be fine. First things first, we need to know how many people we surveyed, which was 100. We circled it here. Okay, so if we surveyed 100 and our final digits are 0 through 9, that is 10 categories. So that means 100 divided by 10 should give us 10 numbers in each category. So I should have 10 people that are reporting 0 as the last digit, 10 people reporting 1 as the last digit, 10, 10, 10, 10, 10, right? Okay, so when I go along here, frequency, these are going to be the observed frequencies, and what these 10s are is the expected frequency. Okay, so we can expect that approximately 10 in each category. Obviously, that's not the case here, but that's what we expect. Okay, so what we're going to do is we're going to calculate this. We're going to do the sum of all the observed minus expected squareds. Okay, so I need to take my observed ones minus the expected one and square that number. So 46 minus 10 is 36, and I'm going to take that guy and like square it. I'm going to get an answer, and I got to use the calculator. Give me a second. Okay, 36 squared is 1296. Okay, then I do the same thing. 1 minus 10 is negative 9 squared, which is 81. Okay, and the negative goes away. 2 minus 10 squared is negative 8 squared, which is 64. 3 minus 10 is negative 7 squared, which is 49. This is again going to be another 49. Okay, 30 minus 10 is 20 squared, which is 400. I'm doing some of this stuff in my head. 4 minus 10 is negative 6, which is 36. 0 minus 10, that's 10 or 100 after you square it. This is negative 2, which becomes 4. And this is another 7, which becomes 49. So there is that. So that is all the O minus E squared stuff. Now this guy says the sum of them. So I need to take the sum of those numbers and add those all together. So you're going to have to give me a second so I can do that. Check me on this if you have a calculator out. It would be a really good idea to do that. 64, 49, 46, 100, 449. Okay, I got 2148. No, 2128. 2128 for my sum. Okay, and we'll pretend for right now that maybe that's correct, because maybe it is, but I'm not going to recheck. Okay, so our chi-squared value is 2128 divided by the expected, which is 10, right? Our expected frequency was 10 for those guys. Okay, and so I'm going to, let's see, 2128 divided by 10 is 212.8 if we divide. Oh, wait a second. Yeah, that's right. Okay, 212.8. Okay, that is a huge chi-squared value. That is massive. 212.8. Wow. Okay, so we've got to figure out where he lives in relationship. So we just got our test value is 212.8, and we've got to figure out where our number is from the chart. Okay, so the chart that you're going to be using is this guy right here, chi-squared. So find him. You'll need him. And we need to know our degrees of freedom. The n that we're using is 100, okay, because we had 100 people that we were choosing from. So our degrees of freedom would be 99. Now, we don't have a 99 on this chart right here. So we go down to where we say 90. Even though 99 rounds up to 100, we never assume more accuracy than we have. So we have to round down to 90, and we go over to 0.05 is the one that we're going to use. So down here, and we're going to find 90 going over, and it's 113.145. So actually, in the grand scheme of things, our 228 wasn't that bad, or whatever our number was. 113.145 is what our chart number is. Okay, now, our test value is still here all the way out to the right side, 212.8. So we are in the reject region. Okay, so like if they were equal to, we would have a range that was in this section. So we're going to cross this guy off. We're going to say that they're not equal to. So we would reject the null hypothesis, saying that they are equal. And our claim here in this case is true, that they are different. So yes, ending digits have different frequencies. Okay, just like that. Ending digits have different frequencies, just like that. Okay, just like we assumed, you know, the 46 and the 30 are lots bigger than the other categories. So there is how that breaks down. Okay, all right, example 2 is kind of the same thing, but in this case, these percentages are not all the same. Do I do one like that to you on the homework? Let me see. No, I don't. I might skip that example just because you won't ever have to do one where they're not all equal frequencies. Like this one is starting off kind of like the oh, what was I going to say? The loaded dice example, where a 1 is occurring more frequently than all the others. So maybe we'll skip this example and we'll go and do a homework problem instead. Okay, so this would be the same type of thing, but I'm not going to go through and do, because it's a little bit more cumbersome when you're doing these calculations when you have like different percentages that you're working with. So I'm going to skip example 2 because I don't think I give you on the homework assignment, I don't think I give you ones that are different percentages all the way across. Like these, everything was 10, 10, 10, 10, 10 all the way through. Okay, you would treat it exactly the same, but I'm not going to go through it for this one. Let's go to homework example number 1. We'll do this one together because they don't give you any data. We're just using this summary information to write our conclusion, and then I'll kind of talk about some things that you need to underline for some of the other problems. Okay, so number 1, 760 subjects. We know that is n. Let's see, 760 subjects. Then why do they say my degrees of freedom is 6? Oh, I know why. Okay. All right. We're asked whether, let's see, identify the days of the week that is best for quality family time. Okay. So days of the week means that we have 7 categories. So I think they call that K maybe. K in this case is 7. All right. So, let's see, that is kind of confusing because now they're going off of degrees of freedom being off of the number of categories. So I wonder if on here, I bet you we did that wrong. Our degrees of freedom should have been, in this case, 9, because we had 10 categories. I think maybe we did that wrong. Instead of using 99 as our degrees of freedom, we should have used 9 because of the 10 categories. So maybe I should switch that. So our number from the chart, instead of being 113.145, it should be 9, going off of the 9 number. Now, it's not going to matter. Our results are going to be the same, but 9 going over, oh yeah, now we're way off the chart. So 16.919 is our number. So fix that. Sorry. 16.919, because we have 10 categories and not going off of the 100 people. We go off of the number of categories for our degrees of freedom. So 16.919. Now, 212 is still way above that. So we still have the same result here, but in some cases it may make a difference. Okay, so change that on your notes. Sorry about that. All right, here we go. So 6 degrees of freedom based on the number of categories, which was 7 days of the week. Okay, consider the claim that the days of the week are selected with a uniform distribution. So we're assuming that all of these are happening 1/7, 1/7, 1/7, equal amount of things. So if I take 760 and divide by 7, let's see, 760 divided by 7, I get 108.57. That's what they got for expected frequency right here. That's how they got that information, okay? And it's based on, like, if we would ask 760 people what day of the week was best for quality time, about 108 people would say Monday, 108 people would say Tuesday, 108 people would say Wednesday. Now, is that necessarily true? I think probably the day of the week that's the best for quality family time is maybe like Sunday, right? Or Saturday even, because, you're home with your family and there's no ball games going on like there are basketball games during the week, that type of thing, okay? So some people might be more led to believe that it's a certain day of the week, but we're assuming that those are equal in value for the time being. We just have to do our test statistic they came up with based on the results of the test, which we don't have the results. We only have the summary of it, is this guy right here. And our critical value was 12.592. Okay, let's see where they get the 12.592 from. Okay, they have degrees of freedom was 6. Let me go back this way. Degrees of freedom was 6. And they went over here 2.5% or 0.05 as their fish value, so 12.592. That's where they came up with that information from. But our test value is all the way outside of here. So what that's going to mean is that this is going to be a reject H naught, and a reject is going to be that they are all equal. So test the claim. Okay, well, let's put in our claim and our hypotheses and stuff. So H naught, H1, we're going to say that P1 is equal to P2 is equal to P3. And how many of these do we have to do? There are 4 days in the week, or 7 days in the week, 7 days in the week. So we're going to assume that all of the percentages or all of the people are choosing those with equal frequencies throughout the week. And let's say days chosen with different frequencies. Okay, so the fact that our number lists outside of here means reject H naught, which means that these people are choosing their favorite day for family time with different frequencies. So they're probably led more to believe that like a Sunday is the best day or something of that nature. Okay, they're not equal frequencies. Okay. All right, so number 2, I'm not going to do this one for you. You guys can figure this out. Your test value, you're going to go off of the example that we did here. So look at this one, the last digits of weights, go off of this example to run this test, but let's underline some important things, and then I'll set you free, okay? 100 people, 100 checks, I guess we're writing checks, okay? 100 checks, and we're talking about like the cents portion of the check. So there are a lot more checks that are written with 0 to 24 as the cents portion. So like if you're writing a check and you're writing it for $100, right? Like that would go into the 00 category. Okay, if you're writing a check that's like $103.52, that would go in this category, right? So I'm guessing the thing that they're trying to get at is that this is happening with the most frequency, meaning that people are just rounding their checks off at the nearest dollar. By putting it as a 0. And that's why this is such a large frequency in comparison to the others, okay? So that's kind of something that we're testing here, all right? We have 4 categories, which means our K is 4, okay? Which means our degrees of freedom would be 3 because they're going off of the number of categories, not the number for your N, okay? Significance value is 0.05. Let's talk about what each one of these numbers should be. If we have 4 categories and we have 100 as our N, we would divide those, and each one of these should be 25. Okay. All right, now the next thing, so this is going to be our observed, and this is our expected. Okay, we can expect each one of them to be 25. So you need to go through and you need to calculate your formula here. Observed minus expected squared over the expected. So this number would be 25, and you're going to do all of these, subtract and square them and all that good stuff, okay? Your hypothesis is that we have 4 P's, so the cents for each one is going to be the same, and your H1 is that categories occur with different frequencies. Okay, so fill out your test value after you calculate them here. Fill out what your critical value is off of the chart, and then tell me your result. Are they occurring with equal frequency or different frequencies? Okay, all right, and go through and do 3, 4, and 5 that same way, and hopefully you shouldn't have too many questions. But if you do, help each other out. See if you can come up with a consensus on what should be correct and not, and that is all.